Merging two independent AI context windows forces a quadratic expansion of data states. The effort required to map every point of the first context against every point of the second grows by the square of the total input. This is a product of matrix multiplication. To cross-reference two arrays of length n, the hardware must perform n-squared operations. Quadratic scaling acts as a physical ceiling for transformer architectures. Once token counts reach a specific threshold, the memory overhead requires more silicon than can be efficiently addressed in a single cluster. Standard network designs assume that the tensor product is the only mathematically valid way to merge these data states. Relying on discrete matrix pairs makes the merge cost a variable of the context size. As long as this relationship exists, raw compute power will eventually lose to the scaling of the data itself. The bypass to this bottleneck is found in the Atiyah-Segal topological quantum field theory, or TQFT. TQFT models complex data boundaries as geometric surfaces, allowing a context merge to occur as a perfectly smooth, continuous union. This framework is formalized within the Gnosis source code as the Atiyah-Segal cobordism functor. By translating data arrays into geometric surfaces, we change the algorithm required to combine them. We move from tracking individual elements to evaluating the evolution of the surface itself. This shifts the complexity from quadratic time into a constant time O(1) topological operation. This mathematical pivot allows software to sidestep the physical limits of hardware silicon by changing the nature of the merge task. Executing this requires mapping digital memory into a specialized topological domain called state space A. Space A is defined mathematically as the polynomial ring f2 of x modulo x squared. We represent it as this binary two-coordinate vector. These coordinates operate under Boolean arithmetic. In this system, adding two identical values returns a value of 0. This utilizes the cohomological property where x squared equals 0. Two identical non-trivial states colliding in this space mutually cancel out. Conversely, when a state interacts with a unit of 1, it preserves its identity. This Boolean cancellation property prevents the compounding values that cause traditional tensor products to grow. Constructing this specific mathematical space allows the system to process merges at O(1) efficiency. Within space A, we use 1+1 dimensional cobordisms to dictate how data boundaries evolve. This cylinder represents the identity function, bridging two separate circular boundaries. Morphing the cylinder into a rounded dome or cap represents the generation of a unit state from the vacuum. A Y-shaped manifold, known as the pair of pants, shows two input circles merging into a single output. The Atiyah-Segal file formalizes this merge with the algebraic notation shown here. The pair of pants cobordism is the geometric equivalent of the multiplication operator, mu. While a traditional tensor matrix is a dense grid of crossing lines, this geometric intersection is a smooth, unified surface. By shifting from arithmetic to geometry, the system resolves structural complexity through shape rather than iterative calculation. For this to work, topological routing must be deterministic. The result must be consistent regardless of the order in which contexts are merged. This consistency is guaranteed by the Frobenius identity, also called the snake relation. The snake relation proves that different ways of decomposing a complex manifold will always yield the same algebraic result. Reversing the order of operations in this chain maintains the exact same output boundaries. The Lean4 source code mechanically verifies this identity across the 16 elements of the tensor product. This verification ensures the genus 1 cobordism has a unique value. The routing order cannot alter the final state. This mathematical stability allows the framework to function as a reliable routing algorithm for massive data systems. We can now apply this to merging language model context windows. Each window is mapped onto one of the input circles of the pair of pants manifold. A traditional architecture would require a quadratic tensor product to reconcile these two datasets. Seen side by side, the paradigms are distinct. On the left, discrete matrix processing. On the right, single-step topological evaluation. The topological side resolves in constant O(1) time because the merge is calculated as a single algebraic product. Chained merges collapse instantly due to the associative properties of the Frobenius algebra. The context bottleneck arises from the specific mathematical tools used for state merging. Treating data as a continuous manifold removes the quadratic penalty inherent in discrete matrices. At the network level, TQFT rules simplify complex, branching data structures. Applying this framework to system architecture allows it to collapse redundant data pathways in real time. As the network grows, these rules prune redundant tensor paths. This geometric reduction bounds the total computational load of the system, regardless of the number of contexts being managed. Structural complexity no longer leads to a compute explosion when data is treated as a manifold. The solution to the scaling crisis is found in geometry. Traditional hardware scaling faces strict physical limits. Topological optimization, however, decouples the volume of the context from the cost of the merge. Mapping context to Frobenius algebras neutralizes combinatorial explosions mathematically before they reach the processor. This is a transition from the era of brute force matrix calculation to topological routing. Scaling intelligence does not require larger supercomputers. It requires realigning the geometry of our data to fit the grain of the substrate.